fragment working. How do I? Well, okay. Seems okay now. Oh, wait, this is. What's going on with this thing? This one? Okay, I think we are set up. So, any question from this time? Oh, I need to load here. Okay, any question from this time? So, this time, I believe we go through quite a bit. So, we are still on this density matrix discussion. And this time, let's see, quick review. We go over this experience of quantum mechanics again with density matrices. So now we have Hilbert space and the density matrix operators on Hilbert space. So basically the matrices on Hilbert space, and they need to have trace one, and they need to be PSD. And then you evolve density matrix by symmetry it with U and U dagger, where U is a unitary matrix that correspond to your physical system evolution. And then when you do measurement, so you still have the measurement operators, and your density matrix also gets symmetry by the measurement operators. So for outcome M, your density matrix will become N, small m rho, and small m dagger. And this is some anomalous state, so the probability is the trace known of this thing, so basically the trace. Trace of this thing is the probability, and the actual outcome state is this thing normalized, so divided by the probability, so divided by the trace. And then from the ensemble interpretation, we have this extra weird example, weird knowledge where you can describe doing a measurement but not knowing a result. Then your outcome state will be all the subnormal state together, and this will actually be a normalized state. So your rho prime becomes this sum m and rho and dagger. And once again, we have an entangled state. And here we give the easy definition where entangled state is a state that isn't written as a tensor of everything. Okay. And then we talk about equivalence of different example. Here, I guess the takeaway is different example can give you the density matrix. In particular, I think this is you proving homework. In particular, all orthonormal bases. So in two-dimensional, every orthonormal basis, when you add them in one-half mixture, they all give you this totally mixed state. And then we have a characterization of which kind of ensemble will give you the density matrix. And we see that they need to be related to this kind of unitary transformation. So psi tilde I need to be equal to phi tilde j, summation uij. And where phi tilde and psi tilde is a notation to combine the probability and the state together. So it's the square root of probability times your state. So it's a non-subnormalized state. And I would say the proof is quite annoying. There is a whole bunch of so I believe the small mistake. So there are actually 4 things that didn't match. Okay, so there are a lot of things that a lot of number doesn't match, that make the proof a bit of unnecessarily hard. So so there are actually three important numbers, but anyway there are four numbers. So one is how many number of states there are in this PI set, and how many number of states in this QJ set. So number stay in in this PI set, and the number of states in this QJ set. So this I and the J, that can be different number, and they can be also different from the dimension of the state. So the dimension here is 2, and there is another thing that can be different. That's the rank of your density matrix. So when you actually do a proof, you see that you want to diagonalize the actual density matrix, and there can be a rank to the density matrix, and it can be not full rank. Okay, and yeah, so there are like 3 or 4 numbers that are different, and when they are different, there are a whole bunch of zero you need to deal carefully, but they can be dealt with, and yeah, in the end you prove the theorem. Okay, and then we talk about reduced density matrix. Okay. So here, I guess the actual important thing is this partial trace operation. Yeah. So partial trace is very important. So the idea here is that we have a joint system, and so joint system and B, they might be entangled to each other, and we find out that if we are only doing operation on A, or if we are only doing measurement on A, then actually we can just describe that by thinking about a density matrix on A. So even though it's entangled system, so you're doing things on A will kind of affect the whole thing. But you can, if you are only dealing with A forever, then you can think about what you do by just considering a reduced density matrix on A. And a density matrix on A, and that's called a reduced density matrix. And the reduced density matrix is calculated by doing this partial trace. And so this time we go over this definition of partial trace operation. And so we give the very basic example definition. So we define the partial trace. We define the partial trace on computational basis. So we say if you are on a computational basis, against matrix IJKO, and when you do partial trace, so the B part will get traced away, so it will disappear, and you're just left with A part IJ, and but the B part need to match also for you to left with anything. So you need to have K. If K equal to L, then you are left with IJ, and if K not equal to L, you just get 0. Okay. And then you can extend this definition to any matrix on the AB part, then yeah, by linearity like this. And you see that this actually matches the idea you have for trace. So you have A1, A2, tensor B1, B2, then you see this is just A1, A2. You can easily calculate that this is A1, A2 times the inner product with B2, B1. And yeah, so here we have some example of doing this. So you see that this beta 00 state is an entangled pure state, and you can write down its density matrix. There are a lot of terms, and when you do partial trace, you see that you have a totally mixed state on the A part. And I believe this is also one of the homework. He can ask you to check all Bill basis. All Bill states, yeah. And to make this more like partial trace, we have another equivalent definition here. And so you are thinking about, so you see when we say trace A, we are basically, so trace has a multiple definition. You think it's a summing over diagonal element, and when you write out a summing over diagonal element, in algebra is a summation I and symmetry A with all the basis, also known basis I. And so you can think about doing partial trace is you are summing over those I only on the B part. So basically partial trace will be same as Your symmetry is rho AB with identity A tensor is bra I and I tensor is ket B. Sorry, bra I on B and ket I on B. Yeah. Okay, so that's a quick recap. Any question? If not, then let's try to finish this chapter today. Okay, and so we have convolutional theorem. And the first theorem, actually, we have a more formal discussion in the book. So if you want formal discussion, it's in the box 2.6 of the book. Okay. But I didn't write it here because I think the intuitive discussion here is a bit more interesting. Okay. So the theorem, what I want to say is a theorem that we can reduce density matrix to. So we want to say reduced density matrix describe all measurement outcome on the subsystem. And this is well, it's kind of proof for nothing, but anyway, let's write the CF here. Okay. So if you want a bit more formal discussion, then please see the book. It's box 2.6. Okay. There is a more formal discussion here. But anyway, so here we give a more intuitive discussion about why this is true. Okay. Yeah. So we claim that. So we define this partial trace operation, and we claim that it give you this density matrix on A, and you should describe everything you want to know on the system A. So in particular, you do any measurement on it, this reduced density matrix will describe it. And the proof is that this is kind of physical. So we think about A and B system. And remember, entanglement doesn't care about physical distance between the system. Entanglement can be, in the world of Einstein, is speaking action with distance. It just happens instantly, no matter how far away you are. Okay? And so we can think about we put A and B really far away, and there is no singling between each other. And yeah, so since there is no singling between each other, so you can do whatever on B that doesn't change with what you do on A. And in particular, you can do measurement on B that doesn't change on A. Okay, so if you do measurement in B in computational basis, and then we see that A will collapse into the reduced density matrix. Why? Because when you do measurement on B in computational basis, in particular, so this part, this is something we have been using. Okay, so this thing is something we have been using in our argument quite a while, and it is something the book has a bit more formal argument in box 2.6. But anyway, we have been argued that when you do measurement on B, then the operator on AB system is you have the whatever measurement operator on B, and then just tensor identity on A. Okay. So you can check it out. This is a measurement operator, and yeah, intuitively this is what the corresponding measurement operator should be on AB. So you do nothing on A, and then you do the measurement on B. Okay. And anyway, so those are the measurement operator corresponding to you do computational basis measurement on B. Okay. And they want to see, okay, so you B, you do this measurement, then what happened to the whole system. Okay. And the whole system should collapse into an ensemble state, like we have always do in this chapter or this section. Yeah. And yeah, so you have different measurement outcome rho I with different probability pi. And so we know the subnormal state will be this pi times rho I. And as we just reviewed today, that should be this M rho A B M dagger. And here M dagger is M because this projection M measurement. So so subnormal state will be this I tensor projected on I, then rho A B, then I tensor projected on I. Okay. And here we do a kind of operation that seems a little illegal, but you can check it out. It's actually true. Somehow this is some kind of magic in Dirac notation. So you think about B part, so you can kind of separate this I-cat here and I-bra here and bring them here. Okay? And yeah, because when you think about you apply this thing on row AB, then the B part will get like sandwiched by those two I and left with those two I. So you see that you always left with this projector on I, this I-cat and I-bra. Okay? So we can kind of move things around and they actually correct. So you separate all these I-cat I-bra here and to become a tensor product with projector on I and left with the other part. The other part is this I-tensor I-bra and row AB, then I-tensor I-cat. Okay. And so let's do a little sanity check to make sure we are doing things correct. So the whole thing should be, when we write this, whole thing should be still in, this should be still in like AB part, right? So it's still in L of HA, tensor HB. Okay. So yeah, what I want to say this is a matrix operator on HA and HB, and here then we see that it's still a good thing. So this thing is in LHHA. Okay, so maybe okay, so I have too much notation. So the only thing I want to say is here we have both AB part because this is AB matrix, this is AB matrix, this is AB matrix, and here then we have the matrix on A, then tensor matrix on B. Okay. So we are still on AB part, so the dimension check out. That's all I want to say. And anyway, so we're thinking about this thing, and then so you measure on B, then you get turned into a whole bunch of these matrices, and then we get rid of the B part because the A doesn't actually know the measurement outcome. Then the matrix on A part, so the tensor, the matrix on A part is just this thing, right? And okay, so the yeah, so the ensemble on A part will just be this matrix. This I tensor I-bra and row AB I tensor I-cat. And yeah, and when you add them together, then you see that this is the definition of the partial trace we had before. So it's this thing we just added here. Okay. So we see that if you B do measurement and never send the measurement outcome to A, and then the density matrix on A will just be this reduced density matrix where you trace all the B parts of your row AB. Okay, so here is hopefully more intuitive proof of why doing partial trace give you the reduced density matrix on the other part of the system. Any question? No? Okay, if there is no question, then let's go to the next topic. Okay, we should be on schedule. Okay, so this is okay. Yeah. So streaming coefficient or streaming decomposition. Okay. Streaming decomposition is a way to describe entanglement. And so we have jumping ahead a little bit. So we have streaming decomposition and purification. And I guess okay, the ordering is a little annoying. Okay, so let's talk about streaming decomposition first. And it seems a little unconnected to other parts, so we're going to be talking about density matrix. But streaming decomposition is something that describes entanglement of pure state. Okay, and so that seems a little unconnected to everything, but you will soon see that this is actually a good way to describe. It's very related to everything about density matrix, because density matrix has a lot to do with entanglement. Okay, and anyway, so streaming decomposition is a canonical form of entangled pure state. Okay, so it's entangled pure state. And yeah, so it's quite important. We have pure state here, and we'll justify this very soon with the purification. Okay. And so anyway, what is the streaming decomposition? Is you have whole psi AB on two parts, and it's a pure state, and it might be entangled, and and this entangled state, we say that so whatever psi AB, we can rewrite it in this form. So psi AB equal to summation A, some coefficients lambda I, and IA tensor IB. Where those, so the important part here is IA and IB are also normal states. So IA is also no basis on A, and IB is also no basis on C and B. Okay, and okay, so you kind of think that this is just a usual superposition linear combination writing of pure state. So what's important here is that I guess IA and IB are okay, sorry. So IA and IB are also normal state. Okay, so that's okay. But what's important here is that everything shares the same I here. Okay. So you are summing over the same I. You are summing over only one I. Okay. So same I here. And what's important here is you can compare these to if you are doing a brute force decomposition to, like, say you decompose psi equal to center basis, so the A part and B part, into computational basis, then you will write this psi equal to some JK, some coefficient AJK, and computational state J and computational state K, right? This is the usual, this is like the most general writing you can have without knowing the streaming decomposition. Okay, you just decompose into computational basis, you get this. And here you see you have two indices here. You have a sum over J and a sum over K. And basically, if you think about A is d-dimensional, B is d-dimensional, then you have like d squared terms here. You have d squared different AJK terms here. But in the streaming decomposition, you only have d terms. You see, so this IA is a basis for d-dimensional space, so you should have at most d. So you should have like d different vector here, and IB should have d different vector here. But you are going over the same I, so you only have a d different lambda I here. Okay. So it's a much more succinct description of the of your pure state, entangled pure state. And okay, and there is a little more about those lambda I, and those lambda I are called streaming coefficients. And let's specify lambda i's all greater or equal to 0, and summation of lambda I square equal to identity. And this summation of lambda I square equal to identity basically comes from normalization. So we think about non square of psi b equal to 1 and lambda I square equal to 1. And lambda I greater or equal to 0 is kind of trivial, because if it's not equal to, if it's not positive, then it has some phase, then you can just, because you have freedom of choosing I and IB here, you can always kick the phase equal to I into I and IB. But we will prove, and we'll see very soon. And anyway, so this thing is very cool because first of all, it's more succinct, kind of more succinct than this. Although here the streaming composition, so this I and IB will be determined by, will depend on psi AB. So kind of you are not losing information, or you are actually describing the same amount of information. So instead of like having alpha JK or d squared terms here, you just have d different lambda I here, and those I and IB that have direction will depend on your state. So you need to describe this I and IB basis also. Okay. So it's a different description, but the most useful thing is about this will describe the entanglement, okay, of the state. So I guess in particular, if you think, so there is going to be a distribution of those lambda I, right? And a special case is when your lambda I is very concentrated, it's a 1 0 0 0 0, then you see you just have one term of this summation, and that will be not entangled state. Will be just 1A tensors on 1B, and that will be a pure state. And in other direction, then you see that when you have a very entangled state, for example, you have this beta 00 is 1 by square root 2 0 0 plus 1 by square root 2 1 1. And then you see that you have lambda I equal to 1 by square root 2 and 1 by square root 2. And lambda I is very evenly spread out, and it's a very entangled state. And yeah, so you see, so this is an example of this is in work. So you have IA and IB just in standard basis. So you have 0 0, then 1 1 here, and 0 also going to 1, 0 also going to 1. And the coefficient lambda is 1 over square root 2 and 1 over square root 2. Okay. And I guess it's good to see another example of how this characterizes entanglement. This is something we did before. Okay. And yeah, so you see that this beta 00 is a pretty entangled state because the coefficient is evenly spread out. And not so entangled state is for the plus state, so another EX is a plus state, tensor plus state. Okay. So if you write this in computational basis, then it's a whole mass. It's 1 over 2, then 0 0 plus 0 1 plus 1 0 plus 1 1. So you see there are a lot of coefficients, and you are not sure it's entangled or not. But when you write in the Schmidt coefficient, then you actually become just the summation of 1 and plus tensor plus. I guess I don't want to write summation here, okay, because there are only one term. So if this thing is 1, then plus tensor plus 0 minus tensor minus. Okay. And yeah, so you see the streaming coefficient here is 1 and 0. And so it's very concentrated, and it's actually not entangled because it's just 0 tensor 0. Sorry, it's just plus tensor plus. Okay. So let's write this out a little bit. Okay. So this is just plus tensor plus. And yeah. And so you so if you input is this 1/2 of everything mixed together, sorry, everything equal superposition of all the computational basis state, and then you do the streaming then you try to find the streaming decomposition of this state, and you will find out it's actually plus tensor plus, and yeah, then you see it's actually not the entangled state. Okay, it's actually a product state. And you find the streaming basis is I and IB is a plus minus basis. Okay. Okay, so that's example and idea of the streaming decomposition. Any question before we go to the proof of construction of how to find it? Okay, hopefully people got some intuition about this. So and yeah, then let's do proof. So why can we always find the streaming decomposition? The proof is actually pretty easy or short because the hard part we all do in linear algebra. Okay, so we start with this general state. So psi equal to the summation jk, ajk, then j state and k state. So this is the general way you write whatever state, whatever pure state between A part and B part. And then we do this linear algebra manipulation of singular value decomposition. Okay. And yeah, we didn't give proof about this, but I just can that this can be done. So for any matrix A, so now we have this. Okay, so this small a is actually a matrix. So we think small a is a matrix such that it's jk's element. So this is a matrix where it's jk's element equal to ajk. So like this. Okay. So on a jk's element you have ajk here. Okay. Like a11 and add, something like this. Okay. So we define this matrix A, of AJK. And anyway, so back to singular value decomposition, it's very similar to diagonalization, but it's more general. It can be done on any matrix. Remember we say, so diagonalization, we say if you have a unitary diagonalizable matrix, then it actually equals to some U, D, U dagger, okay, where D is diagonal. Okay. And the singular value decomposition is very similar, but you don't have the same U here. So you have a U here and a V here. So the U and V are different matrices, but they are unitary. And D is a diagonal matrix. And so this is very general. Actually, A don't even need to be a square matrix. It can be any matrix. Remember, diagonal. If you want to diagonalize a matrix, they need to be a square matrix. But you can even have like different dimension of A, and you can still do a singular value decomposition. So this is very general. Yeah. And because you have the extra freedom of U not equal to V. And anyway, it just turns out this is possible for any matrix of any dimension. You can do singular value decomposition and get UDV. And so D is diagonal with diagonals greater or equal to 0. And this is also something extra from the eigenvalue from the usual diagonalization. So usual diagonalization, the eigenvalue can be anything, not necessarily greater or equal to 0. But here, singular value, you can also always make a greater or equal to 0 because you can push the extra phase equal into ULV. Okay. And yeah. Anyway, that's some digression. And so from here, then we're basically done. We just need to group things together. Okay. So what happens is, well, we write A, so you have an algebraic expression here. So A equal to this 3 matrix UDV. And then we write this in terms of the component. So as we said, so this AJK is JK's component of this A matrix, and that's the JK's component of the product of those 3 matrices. So that should be UJI and DI times VIK, and summation over I. Okay, so we just break AJK equal to So we just break A of JK to this of JK. This is what we do. And yeah, so usually here you need to put in 2 dummies. So you have summation I and summation I prime here. But you know D is diagonal, so D here you just need the same I here. So you have DI. Okay, so I will equal to I prime basically. So yeah, so this expression becomes this expression just by the singular value decomposition, and then we just group different things together. Okay. So we have so we group the summation J together. Only thing dependent on J is UJ and J, and the summation K together is this part and this part. Okay, and yeah, and we call this thing yeah. So we deal with the summation J, and we just call this thing. So this thing is something dependent on I, because J got sum over and we leave at I. And we call this state I of A, and similarly you call this state is also dependent on I, you call this I of B, and then we call this Di as lambda I. And basically we are done. So we are in this form now, right? So psi is a summation lambda I and IA and IB. Okay. And so we need to check a little more things. So first we need to have lambda I greater or equal to 0. Then it comes from D is greater or equal to 0. So all the diagonal elements are greater or equal to 0. Okay. So once again, D is a diagonal matrix. It looks like D11, D12. Sorry, D22, D, D, D. Okay. Okay, this is a little weird notation, but I should use big D, whatever. Yeah. So D is a diagonal matrix, and we say it's greater or equal to 0, so all diagonal elements are greater or equal to 0. So I'll give you the lambda I is greater or equal to 0. And you can easily check the normalization. You just normalizations come from the normalization side, so that's don't need to check. Yeah, and I guess then we need to check I and IB. So those states are also normal bases. But remember, they come from like this J and K, and basically get expanded by unitary operator U and V. And yeah, so this I and IB is just the computational basis acted by unitary transformations, so it's also normal. And similarly, IB is also normal. Okay. And yeah, so that's the streaming decomposition. And it's easy to show that it's unique too, and but let's skip it here. Okay. Okay. So any question about this proof? So yeah, basically you do singular value decomposition on this coefficient matrix, and then you do corresponding, and you group terms to your J and K, and you find out that you find your streaming basis, and get your streaming decomposition. And okay, so some notation that I have been using without definition. So I and IB is called a streaming basis. Hopefully, I should put a set here. So the set IB and the set IA and the set IB are called the streaming basis. And the lambda I is called streaming coefficients, and they will characterize entanglement. And here the motivation we already talked about. So once again, you have plus state, tensor plus state, and it looks like 0, 0 plus 0, 1, 1, 0 plus 1, 1, and times 1 half. You don't know where this is entangled. It looks like a lot of things, superposition of a lot of things. But when you calculate its streaming decomposition, then you see it's 1 of the plus tensor plus 0 of 0 minus tensor minus, and it just plus tensor plus, and it's not entangled. Okay. Yeah, so the streaming coefficient will characterize entanglement. And intuitively, when the coefficients, so those lambda I are more evenly spread out, it's more entangled. And yeah, and as an extreme example, we define that we see that when the streaming coefficient is the most concentrated, so it's 1, 0, 0, 0, 0, 0, then you know your state is a product state. Okay. And and here we have not a very good way to characterize this spread out. So we define this streaming number. That's just the number of non-zero streaming coefficients. Okay. So for example, in this case, the streaming number is 1 because they only have 1 that's non-zero and all other things 0. Okay. And so that's basically, is that rank? Yeah, that's basically the rank of this A matrix. Okay. And yeah, so this streaming number will characterize where your state is a product state. So you see that your streaming number equal to 1, and your state is product state. And obviously it's not 1, it's not a product state. Oh, I guess not so obvious, but you can prove that. Okay, yeah. So it's obvious that if the streaming number is 1, it's a product state. If it's not 1, then you can do some work and prove that it's not a product state. Okay. So yeah, so this is a very rough characterization of how entangled your state is. But it's not very robust because you can have like 0.9999 and 0.1111 on all the other coefficients. So you have a very small amount of all other coefficients. And you will say your streaming number is very large, but actually that's very close to a pure product state. So yeah, so this is not very robust definition by something. And if you read the later chapter of the book, you will see that there are better ways to characterize how spread out your streaming coefficients are, calculate the entropy, etc. Okay, we'll be short on time. Okay, let's go a little ahead. And something about streaming number. So you see that the number of lambda here is equal to the number of basis state. I guess the number of bases that actually touch in IA and the number of bases that actually got touched in IB. And those, so both of them, so this should be smaller than dimension of the A system, and this should be less than the dimension of B system. So you see the Schmidt number is at most the smaller of the dimension of the A system and B system. Okay, 10 minutes. Okay, 10 minutes. We should have. Okay, let's try if we have enough time. Okay, if no question, then let's go to purification. Okay, so this is where the. Okay, then we back to our business of density matrix, and then we'll see why we talk about the streaming coefficient. Okay, so purification, let's scroll back a little bit. It's like a reverse operation of calculating reduced density matrix. So we think about, well, although it's a little weird. So when we talk about reduced matrix, we come from actually come from row AB. Okay, row AB and then we say we can get row A and row B. Let's say we get row A, and but if we start with a pure state, then we will get row A. And then we have like a reverse operation of this is you have a row A, then you can always find the pure state side AB that will, when you do reduced matrix, when you trace out B, you will get back to row A. Okay, and yeah, so that's what we want to do. So given some row A, then we want to find the pure state. Okay, so pure is important here. Okay. So we want to find the pure state such that this pure state, when you trace out the reference part, so we say psi AR, so R for reference. So we trace out the R part of this pure state and we'll give you this row A. Okay. Okay. So it's kind of like a reverse of partial trace. And so some important thing about here, so this is mostly just a mathematical procedure. Although partial trace is also kind of mathematical, but partial trace you can think of, this is a bit more mathematical than partial trace because as we see partial trace you can kind of think of it as you do measurement on B and you throw out the measurement result. But purification is really there's nothing physical you can do on here. So you got density matrix here, you just imagine there is some reference part that together they will become a pure state. But usually you cannot find this reference system. It's like you have a density matrix and this is something you already throw away. It's kind of the B system that you already throw away and it's really far to find it back. Okay. So this is only a mathematical procedure, but it is very useful because you can simplify a lot of proof because usually pure states are easier to manipulate, although we spend a lot of time in this chapter talking about density matrix, but in practice you like pure state. Okay, and R is for reference system. I guess it's simplifying thing. So one of the simplifying thing is the thing we're just talking about, right? So we have a density matrix here that then we purify it equal to psi AR, then we can kind of analyze the entanglement between psi AR by calculating the streaming decomposition. Right? So it kind of justify both of them together. So say you do purification, then then you can think you can analyze the streaming decomposition of psi AR. Okay. So there is something you can learn here. Okay. And yeah, so this also justifies thinking of basically thinking of everything as a pure state. Because wherever you did a density matrix, then you can do this mathematical operation of purify it. And so you think there is some R system that together with your A system, your state is a pure state, but you just cannot access this R system. Okay. Yeah. And okay, 5 minutes, we should be able to. Okay, and yeah, so the theorem here is every density matrix row can be purified. The proof is quite simple. So you get whatever density matrix A, then density matrix, as we say, PSD is diagonalizable, and then you can diagonalize. So equal to some PI and II. This is some II, some orthogonal basis. And then your psi AR, it can just be defined as summation I square root of PI. and this IA and the tensor whatever orthogonal basis on the R system. Okay. And yeah, so this is the purification. And we can do partial trace on this thing to make sure that it is actually a purification. So trace R of density matrix of this. So summation ij, pi, pj is ij and ir, jr. And then you trace all, so you trace R part of this thing. And because this IR and JR is also on basis, so actually so it's equal to delta ij. It's only equal to 1 when I equal to j equals 0 when I not equal to j. And yeah, the delta function just force j equal to I, and so you have summation I, pi, I, and you know it's rho a. Yeah. And yeah, so you see there's a relation between the streaming coefficient and the eigenvalue of your density matrix. So streaming coefficients actually equal to square root of the eigenvalues here. Okay, so that's pretty cool. Okay. And oh, we have time. So 3 minutes. Let's finish this chapter basically. Okay. And finally, you have the small picture of relating everything together. So we have a picture that describes a lot of things we do here. So we can think about entangled pure state on AR system, and then we know we do partial trace out of R, then we'll get density matrix rho, and then we know we go at purification, then we'll get the entangled pure state AR. And okay, so one thing here is, so the purification is not a one-to-one operation, although we give a specific construction. So actually, many different pure state can get reduced matrix to can do partial trace to the same density matrix, reduced density matrix. Because here you see that you have freedom to choose IR, right? You have freedom to choose IR, and there are actually more freedom to choose here, as you will see in some homework problem, probably. Yeah. But anyway, so this is a many to one, this is one to many, and but we have a particular. We define some particular correspondence here. Okay, so we'll say we'll psi if our psi r equal to the streaming decomposition, summation I square root I b, and then the density matrix will be reduced density matrix will be summation I p I, and I and so this is in a diagonalized form, and it's in the streaming decomposition. Then we have a very nice correspondence here, and so the square root pi will be streaming coefficients, and those pi will be eigenvalue of rho a, and you can think of this as an ensemble interpretation of rho a. Then those pi will be ensemble property. Okay. But as we know, there are many different ensemble interpretations of rho a. So so if on the correspondence, then this needs to be diagonalized. Okay. And so those are streaming coefficients, those are eigenvalues. And okay, so the thing we have been saying, and finally we can say is that, so we see that when the square root pi is very concentrated, so it's 1, 0, 0, then it's product state. And that corresponding to those pi equal to 1, 0, 0, and it's a pure state. Okay. So you see that the purified state is a product state, then the reduced matrix is a pure state. And that kind of makes sense, right? Because if you're product state, then you have some psi tensor psi r, then obviously then the reduced part is just psi a. Okay. And then the reverse of this is that you have an entangled state here, so this is not totally concentrated, and then you have a mixed state here. So yeah, so here from the streaming coefficient discussion, we see that when your state is entangled and then you do partial trace, then you see that your reduced matrix is mixed. Okay, this is kind of what we want to say in all this discussion. But we also hopefully give you some understanding about the entanglement on pure state. Okay. I think that's it for now. Any question? Here we have a little more about block sphere, but we can see that next time. the bus view and CMOS over here, but there's a little extra with a mixed day. Okay. If not, let's see you on Thursday, and also there will be midterm, I think on week 8, so in 2 weeks, and we'll have a midterm also on Thursday because we won the 2-hour class. Yeah, so midterm should be on the same classroom and class time of Thursday. And the range I'm not quite sure yet because we're a little slow. So let's see how we do in a few days, and we'll give more formal announcement about the midterm, range, etc. on e-learn later. Okay. Any question? Otherwise, yeah, see you on Thursday.
Will the midterm be similar to the homework assignments?
Yeah, I think it would be maybe about the same level, or yeah, maybe similar. Yeah. So there should be like hopefully there are some basic parts that's easy concept and calculation, and maybe like 40-30% more challenging question. Should be like that. Yeah. Okay. Yeah. See you on Thursday.